Welcome, everybody, to our tour of the universe brought to you by the Morrison Planetarium at the California Academy of Sciences. My name is Jackie. I am the manager of the planetarium programs here at the California Academy of Sciences, and I'm very excited for you all to be joining us for our tour of the universe. Now, we are going to be using a software called OpenSpace. It's an open source planetarium software funded by NASA that you can actually download at home yourself. Now, our software is pulling data all the time, so you might notice maybe every once in a while it'll be a little bit maybe laggy a bit, or might pause for a second. And that's just because, like many of you, I'm working from home today, and so might have a little bit of a hiccup here and there with Wi-Fi. But hopefully today we will be all set. Now, I like to start our planetarium shows and our tour of the universe relatively close to home. We are looking at the International Space Station, or we call it ISS for short. And the ISS is as far as humans do physically travel nowadays. When we're looking at the International Space Station, it can look pretty small compared to planet Earth, but it is quite large. It's about the size of an American football field, or I like to say the Academy of Sciences. So if you've actually ever been in our building, you have been able to walk from one side of the International Space Station to the other. Now, humans don't just live in the whole space station. We have the sun energy shields that power most of the International Space Station, but we also have these kind of tube-like areas, and this is where humans are living as well as doing many experiments. But today we are actually going to travel much further away from our planet. We're actually going to see how far our human influence has gone. We're going to see how far humans have physically traveled. We'll see how far our spacecrafts have gone, and we will see how far human communications have gone as well. But as I mentioned, the ISS is as far as humans do physically travel nowadays, but there are plans in the works to change that. But as we're zooming away from the International Space Station, it may look like the ISS was actually plummeting into our planet Earth. It wasn't. It was just our perspective and how we're viewing it. We can actually see the path of the ISS around our planet. So that kind of yellowish line shows where its path was as of yesterday. So everything we're seeing in our planetarium software is based off of real data and where everything was yesterday afternoon. So those clouds you see on the daylight side of Earth, that is what those clouds were yesterday. But in the meantime, we can actually see our astronauts traveling very quickly around our planet Earth. It takes them about 90 minutes to orbit us just once. In fact, you can actually see the ISS passing overhead in the nighttime sky. You can look online to find out if it's going to be passing over your area, what time, and where you should be looking. And when you're looking, it should look like a little bright star that's moving across the sky. But let's go ahead and start looking at some of the other objects in our solar system. And let's bring up the path of our closest natural neighbor. And that would be the moon. Now, the moon is as far as humans have traveled out into space. The Apollo astronauts came out here in the 1960s, and it took them 4 days to travel to the moon. Now, even though the moon is close, our closest natural neighbor is actually not close in human terms. The moon is about 250,000 miles away from our planet. And as we get farther and farther out, we're going to go much further. We'll be going distances of millions, billions, and sometimes even trillions of miles. And when we get this far out, it doesn't make sense for us to use miles or kilometers anymore. So we're going to be using a different yardstick, so to speak. The speed of light, the fastest thing that we know about. Now, if we were actually traveling the speed of light, and which is about 200,000 miles per second, it would take us 1.5 seconds to get to the moon. So we say that the moon is 1.5 light seconds away from planet Earth. But let's go ahead and zoom on in a little bit closer to the surface of the moon. Now, the moon gives an illusion that it's actually been hit by asteroids or comets or meteors a lot more than planet Earth. And yes, it's been hit quite a bit, and we're very grateful that it's been taking those impacts. But also, remember, Earth is actually a much bigger target, so we actually get our fair share of impacts. The reason why we see so many impacts on the surface of the moon is because it has basically zero atmosphere. There's no weathering, no erosion, and there are no plate tectonics moving around the planet or the moon. So once something actually appears on the surface of the moon, it's never erased like we see here on Earth. Now, as we zoom on out, we can actually see the path of the moon around our planet Earth in this kind of purplish color. And it takes about a month for our moon to orbit us just once. Or I like to call it a month, because not a full month. It's about 29.5 days. But let's go ahead and bring up the paths of the other planets in our solar system. We'll need to zoom out just a little bit to be able to see those. And we can actually see the sun in the center of our solar system. Now, the sun is our closest star to us. And if we were traveling the speed of light, it would take us 8.5 minutes to get from the Earth to the sun. So it's about 8.5 light minutes away. We can also see the paths of those planets that we know so well. We have, starting from closest to the sun, the rocky planets Mercury, Venus, Earth, and Mars. Further out, we start to see the gas giants, Jupiter and Saturn. And even further out would be Uranus and Neptune. Now, when we get this far out, I like to pause for a moment and take a look at what else might be in our solar system. Now, we see a pretty sizable gap between Mars and Jupiter. We know that there's not nothing there. In fact, we know that there is the asteroid belt. Now, I've brought up only a percentage of our main asteroid belt. It's about 70% of all the asteroids, every little dot. And that's because if I brought up every single dot for every single asteroid, my computer would actually crash. But this gives us a good rough idea of how much stuff is in our asteroid belt. And it's not just asteroids. There is another object that I like to talk about in this area. And I'm bringing up its path, and it might be a little bit difficult to see, but it's kind of that lighter blue colors, and it's showing its path. And this is not an asteroid, but I'm curious if you have any ideas of what this might be. So this is an object called Ceres. Now, the reason why I like to bring up Ceres is because it tells an interesting story of how we have viewed our universe. When we first found Ceres, which was over 300 years ago, We thought it was the only thing orbiting in between Mars and Jupiter. So we thought it was a planet. So we called it a planet. But as time moved on, we started to have telescopes. We started discovering more and more objects in this area. Realized there was a lot of small rocky objects. And so we started calling that actually asteroids. So we changed the name of Ceres from a planet to an asteroid. And this similarly happened to another object in our solar system, and that is Pluto. And I brought up Pluto's path as well. When we first discovered Pluto, we figured out that it was the only thing out there. But as our telescopes and our technology got better and better, we started discovering smaller objects. Some of it was kind of icy objects. Some of them mostly smaller than Pluto, but a couple of them were actually about the same size as Pluto as well. So instead of adding another dozen planets again to our solar system or categorizing them as planets, we decided that we need to settle on what is the criteria for a planet. And they came up with these 3 criteria. 1, it needs to orbit a star. Well, Pluto and Ceres both orbit the sun, which is a star, so check. 2, it needs to be large enough, massive enough to have its own self-gravity pull itself into a round and spherical shape. Well, Ceres and Pluto are round, so check. And 3, it needs to have cleared its path, meaning it needs to have a relatively clear orbit. Now, things can orbit around it, but things can't be in its orbit. Well, we see Ceres goes right through the asteroid belt. And let's go ahead and bring up what we now know as the Kuiper belt, and all those objects that are in there as well. Well, as you can see, Pluto goes right through the Kuiper belt, or sometimes we call them trans-Neptunian objects. So we decided that there needs to be a new category. And when I say we, I'm talking about the International Astronomical Union. And so they decided there's a new category. It's called a dwarf planet. And so Pluto became a dwarf planet. Ceres actually got promoted to be a dwarf planet. And we found a couple more that we have now categorized as dwarf planets. And the reason why I like to stop here and talk about these things is, remember, it's all about our own perspective. As we learn more and more about our universe, we start to put these things in categories, and sometimes they don't fit, but that's okay. It's our own way of seeing the world. And that's going to come back a little bit later. Now, I'd like to continue our journey, because we're just still in the solar system, and we actually need to get to the outer parts of our universe, and we have just a little bit more time. So to help us move along quickly, I'm actually going to turn off some of these objects because they tend to slow down my planetarium software. But let's go ahead and recap how far we've actually gone out into space. So we've seen how far humans have traveled nowadays. We have seen, and that's to the moon, and that's about 1.5 light seconds away from us. We've seen the sun, which is about 8.5 light minutes away. And now if we actually could travel from one side of Pluto's orbit, say over here, and travel all the way to the other, traveling the speed of light, it would take us 10 hours. So we say it's 10 light hours across. And even out here, we can actually check in on our human influence. We've seen how far our humans have traveled. Let's see how far our spacecrafts have traveled. We're now seeing the paths in orange of some of the fastest and farthest spacecrafts. We have Voyager 1 and Voyager 2, Pioneer 10 and 11 that were sent out in the 70s. And more recently, we have the New Horizons spacecraft, which was sent out towards Pluto back in 2015. Now, these are the fastest and farthest spacecrafts that we've sent out into space so far, but none of them have traveled as fast as light travels in a single day. Well, let's continue our journey. We have a little bit further to go. Actually, we have a lot further to go. And now we're going to be traveling like distances of light years. We'll start flying past the other stars in our galaxy. And the closest star to us, well, beyond the sun, is about 4 light years away from us. So it would take us 4 years to get there to travel the speed of light. And even way out here, we can actually check in our human influence one last time. I've brought up this kind of sphere shape grid, and this is representing how far our radio signature has gone out into space. Now, what I mean by radio signature is we sent out radio and television signals for quite a long time, and some of them were still trapped within our atmosphere. But around the 1930s, they were strong enough to escape our atmosphere and start continuously moving through space. This is about 90 light years away from us in all directions. Since remember, radio signatures travel the speed of light because radio is technically light. So when we look at our radio signature, we can also see how many planets we have found this far out. I've brought up a ring around every star that has at least one confirmed planet outside of our solar system, or what we call an exoplanet. If you look pretty closely, there's actually quite a few exoplanets inside that radiosphere. So who knows? Maybe there's somebody listening to Nat King Cole. But let's keep on our journey. We are still flying past the stars within our own galaxy. We haven't even left the Milky Way. And as we do, I want to encourage you all to continue to look and see if you can find that radiosphere. Now, we live in what we call the Milky Way galaxy. It's a spiral galaxy, and then as we're seeing it relatively edge on, it's fairly thin. But let's go ahead and look at it face on. So we can see the beautiful spiral arms. And we are about 2/3 out from the center of our galaxy. And our galaxy is made up of gas and dust and stars. And if we could actually see in the middle of our galaxy, there's a bright group of stars that are very close together. And if we could see past those, the very center of our galaxy, you would see, well, basically nothing, because there's a supermassive black hole at the center of our galaxy. It's about 4 million times the mass of our sun. Okay, can you still see that radiosphere? Can you point towards it? You're all correct, because I have no idea where you're pointing. I'll use my mouse to show exactly where we are. My mouse is just pointing at the tip where our radiosphere is. That's our little, so to speak, corner of the galaxy. Now we are at distances of thousands of light years. Now, if you were to go from one side of our disk to the other, it's about 100,000 light years across. So if we wanted to take a round trip from one side of our galaxy to the other, it would take us about 200,000 years. But our galaxy that has roughly 4 billion stars is just one galaxy out here in the universe. Now, every dot we see is not a star, but its own galaxy with billions and sometimes trillions of stars. And the colors of these galaxies may make it seem like we accidentally spilt some cosmic Skittles in the universe. These aren't the actual colors of the galaxies. They actually show us the different surveys that have mapped them, or the different densities of them. And as we zoom on out, you'll start to notice something a little funny. You might see that our universe is kind of in an interesting shape, like an hourglass, bow tie, or even butterfly. Now, the universe is not actually the shape of a butterfly, though that would be pretty neat. This is, again, because of our own perspective. We are the ones looking out and making the map. This is a map of all the galaxies that we have set down so far. Remember, I told you that everything we're seeing today is based off of real data. And so also remember that our galaxy is made of gas and dust and stars. Well, that gas and dust actually blocks our view. So we can't see beyond our own galaxy. So while we have these kind of great regions where we don't see a lot, and that's because we just haven't mapped that area yet. If we could see past our own galaxy, we should be able to see more galaxies, maybe over here or up to the upper left. But because we haven't mapped it, we're not showing it. You also might notice that it looks like we're the center of the universe. As much as some of us would like to think so, we are not. Again, remember, we are the ones making the map. We are looking out around us, so it's going to appear as if we are the center. If we were to go to any one of these other galaxies, maybe in the upper right or towards the bottom of our screen, and we were taking a picture of our universe, figuring out where everything is, it would appear as if we were the center of the universe. As far as we know, there is no center of the universe. Okay, we have just a little bit further to go. We'll start to see some of the earliest objects in our universe. Kind of these reddish colored marks. And these tell us where some of our earliest objects are, what we call quasars. They're bright cores of some of the first galaxies. And I do mean earliest, because at any time we are looking out in space, we're kind of time traveling in a way. The light of those objects have to travel so far by the time it travels all that distance and gets into our telescopes, we are seeing the light of those objects as they were in the past, not how they look today. So for example, when we looked at the closest stars to us, about 4 light years away from us, that's how they looked 4 years ago, not how they look today. And now we are seeing the universe as it was billions of years ago. And because of that, that means there's only so far we can go. There's an edge to everything that we can see. And as we zoom on out, we'll start to see that edge called the cosmic microwave background, or CMB. Now, if you had a radio telescope and you can actually look in the microwave range of light, you would see this everywhere you looked. In fact, some of the first radio astronomers were really confused because they're like looking up in the sky and what is going on? We're seeing interference everywhere they looked. But soon they realized that it was not interference, but this is the baby picture of our universe. This is the first light after a few thousand years after the Big Bang would have happened. But since this is the edge of what we can see, that means this is as far as we can go. Can't go any further. So it's time to head home. I promise I won't leave you out in space. But one more thing as we're zooming on back home. All that we have looked at today, all these stars and galaxies and the cosmic microwave background, that's not everything in our universe. There's dark energy, this mysterious force that's causing space itself to accelerate as it expands. There's dark matter, some mysterious substance that doesn't seem to interact with light at all, but we see evidence of it in between and at the edge of galaxies especially. And we call all these things dark energy and dark matter because, well, we're not quite sure exactly what they are yet. But we do know that they make up 96% of our universe. So everything that we've seen so far out here is only about 4% of everything that is out here. And that may make us feel a little small, like we're one tiny dot in this homogeneous universe. But I like to think of it this way. Yes, we're one tiny dot. But look at all that we have found, almost entirely by looking through telescopes. And there's a whole lot more for us to discover, and there's a whole lot more for us to learn. And that's what makes it a wonderful time in human history. That we're not just able to talk about our universe, but show you it in 3 dimensions. A map of the cosmos. And we're only just starting to unravel the true nature of our universe. But only just starting. The rest, well, that's up to the next generation of scientists back here on planet Earth. Well, we're back home, everybody. That third rock from the sun. The only place in all of this that we have found life. And that's pretty incredible to think about. So welcome home, everybody. And thank you for joining us for our tour of the universe. If you would like to learn a little bit more about OpenSpace or any of the topics that we've talked about so far, we have some links in our chat box. But also, we would love for you to explore OpenSpace as well. Again, you can download that at home with your home computer. Just go to openspaceproject.org. Pretty sure I got that right. Or sorry, .com. And also, we would love to hear what you think of this program and help us tell NASA the great work that this program does. So if you can fill out the survey in our chat box, we greatly appreciate it. Now, you may have noticed our Earth has changed a bit, and that's because I quickly ran time forward to today. And this is what the Earth looks like right now. And it's not that there's no clouds in that area. It just happens to be that satellite has not gone over that part of the Earth. And so therefore there's no data, and we're not showing you that data. So OpenSpace is an amazing thing to be able to explore our planet and our universe. Thank you, everybody. And I hope you can join us again in the future for another tour of the universe. Good night.